Okay, so Michele, I think we can start because it's now already a few minutes after 9:30.
Yes.
So, okay, I see if you wish, because it's a bit small. Okay, in any case, so this is Lorenzo Amati at INAF, Bologna. You see connected Michele Moresco, University of Bologna, and together with Massimo Della Valle at INAF in Napoli, we are organizing this session, so on non-standard cosmological probes. So we would like to thank you very much, all of you, for joining this session and providing your contributions. I hope it will be, as we are sure, nice, very nice and interesting discussion. As you have seen at the end of each session, so this morning and later tomorrow afternoon, we will have time for discussion. So if there will be no time for questions after the talks, there should be time after the end, right at the end of each session, this later this morning and tomorrow. Each talk, as you see, you have your time. So invited ones are 20 minutes. The contributed are slightly shorter, but so we let you manage your time. We will warn you if you are actually running out of time. So now I leave the floor so I don't see Massimo, so Massimo will join as soon as possible. So I leave the floor to Michele for his welcome address, and thank you very much again.
Thank you. Thank you, Lorenzo. So also from my side, thank you very much for participating to this session. Here, just a quick reminder of the fact that we will have two separate sessions, one today and one tomorrow from 4:30 to 7:30 in the evening. And I provided you here the link with the agenda of the today's, which I also tried to summarize here. Just a very brief word of introduction on the motivation of why we propose this parallel session. The point is that basically since the discovery of the accelerated expansion of the universe, there was a lot of effort, both technologically but also scientifically, to try to understand the nature of this accelerated expansion. And in this search for the reason of this expansion, different probes have been proposed. And we are now in a lucky period in which we manage basically to push this probe to their limit. So to the point in which not only we are trying to understand from a general point of view, which are the constitution of our universe, but also try to pinpoint exactly their values. And it's at this point that interesting things start to come out, because we know very well the tension that are uncovering now between the determination of some cosmological parameter. And the interesting thing from my point of view is that if a few years ago, basically this kind of tension was basically a dichotomy between two different kind of measurement at very early, in the very early universe with very large mission and such as Planck, WMAP2, and measurement instead in the more local universe, so with fades, supernovae. And so if a few years ago this dichotomy would have appeared like this, we have now something like this. And it's very interesting, this kind of plot that I borrowed from Di Valentino et al., because it shows that it's not only the dichotomy between two measurements for which we can try to think if there are some systematic hidden below or some hidden effect, but adding to the data set a lot of independent measurement really strengthen these findings, and in particular open the field to new discovery, to the possible discovery of new physics, and to the determination of the ingredients of our universe. Something similar happens also for the sigma 8 parameter, and this is, for example, the latest result from this year 3 mission. And the important thing is that having many independent probes is really fundamental to try to understand what's going on. And how can we make progress in this kind of understanding? The point is that in the past years, we discovered that the strength is really in the combination between different probes. And this is a plot of a few years ago where it shows the main standard cosmological probe, and so supernovae, CMB and BAO, how they alone, they are not able to pinpoint exactly the values of the cosmological parameter, but it's really the combination between those that allow us to understand the nature of our universe. So this is a kind of plot that we might have a few years ago, and now we have a plot like this. This plot has been taken from Metal 2020, and this is extremely interesting because we are expanding this plot, exploring many different independent cosmological probes. And the importance of adding alternative probes is that, as we saw from the original one, what we have is that different probes are important because they probe different cosmic time, they are sensitive to some parameter more and less to other, and they have different systematics, but we really find that it's the synergy and the combination between these probes that allow us to understand exactly the values of the cosmological parameter. And not only that, the other important point is that having different probes exploring the same parameters allow us also to keep under control possible systematic effects and to try to explore if different probes have some problem or another one. So in this parallel session, what we thought is that it would be extremely useful to have a generic overview of the main alternative cosmological probe that has been proposed in the past few years. So we will learn about GRB, we will learn about quasar, intensity mapping, surface brightness fluctuation, gravitational waves, cosmic chronometers, trying to give not only an overview, but also to foster some discussion about how it is possible to move forward exploring different probes. So this is the end on my side, and I leave again the word to Lorenzo.
Thank you very much, Michele, for the nice introductory address. So now it is time to start the actual session. So I would ask Aliktis Politsodou to take the floor and share his presentation, which will talk about cosmology with neutral hydrogen intensity mapping. Thank you.
Thank you. I'll share presentation. I guess you can see it now.
Yes, perfect. Thank you. Thank you.
So thanks for asking me to give this presentation. I'm going to talk about cosmology with neutral hydrogen intensity mapping. So the motivation for trying to do cosmology with the 21 centimeter emission line, basically from neutral hydrogen, is that it can go further, much further than where optical galaxies can go. So in this nice image here, you see a summary of the history of the universe, and the precision data that we have from direct observations come from two very distinct epochs in the history of the universe. So obviously we have with Planck and previously with WMAP, we have very, very high precision data from the cosmic microwave background, so for the early universe, and then we have precision data from galaxy surveys like SDSS from the late time universe, so for the last 5 billion years or so, where dark energy dominating. But in between that, there are extremely interesting epochs which have not been directly observed. So, for example, the epoch of reionization and the Dark Ages and the Cosmic Dawn, which is basically when the first stars and galaxies were formed. So, what is happening in this gap is basically that during the Dark Ages, for example, there are the CMB photons, but there is also neutral hydrogen, and there are no astrophysical sources, but neutral hydrogen emits the 21 centimeter photons, which are then redshifted. So there are no galaxies to observe, but the universe is full of this 21 centimeter radiation, and it would be fantastic if we could observe it. And then when the first quasars and galaxies are formed, they start ionizing the neutral hydrogen around them. So then the universe becomes closer to what it looks now. So we have many galaxies forming, and there is no neutral hydrogen around, apart from the fact that it still survives, it is shielded from ionization within the galaxies themselves. So there's cold gas, neutral hydrogen gas within the galaxies themselves. So we could use the 21 centimeter emission to also do late time cosmology, so to complement optical galaxy surveys. So basically, in a nutshell, we can cover, in principle, a huge part of the volume of the history of the universe and go down to 0.1 billion years after the Big Bang with neutral hydrogen. So we can do that with instruments like the Square Kilometer Array and its Meerkat precursor that is currently operating in South Africa, and we can complement the work of amazing optical surveys coming up like Euclid, LSST, DESI, etc. So that's the motivation. So, but things are actually not that trivial. So in the sense, if we want to do cosmology, if we want to do late time cosmology with intensity mapping, which is what I'm mainly interested in, and be competitive to surveys like Euclid, we cannot do it the traditional way. So the traditional way that optical surveys work is detecting individual galaxies at the level of 5 sigma or 8 sigma or whatever, their positions on their redshifts. And in order to be, to reach sub% precision, they need to detect tens of millions or hundreds of millions of these galaxies. But doing that with 21 centimeters is extremely difficult and extremely expensive, basically because the signal is so faint. You need a very, very sensitive radio instrument. So to detect a billion galaxies with the SKA, you need SKA phase 2, which is like the complete project, which might happen or might not happen in 30 years from now. So you have to find another way to do it if you want to do precision cosmology now. So the idea is that instead of detecting individual galaxies, which you cannot do with phase 1, Meerkat, etc., you instead just use these instruments instead of interferometers, just use them as a collection of single dishes, which means that you can have a very big field of view. You can scan a huge area of the sky really fast. But then you lose the angular resolution. So you cannot detect individual galaxies anymore. But instead, you can just take 3D voxels, big pixels on the sky and a long time, like big cubes that are basically determined by the resolution of your instrument, which is 1 degree or more. And just collect the H1 emission, the 21 centimeter intensity, emitted from many galaxies together within this voxel. So then you end up with something like the map on the right-hand side on this slide, which is an intensity map that looks very similar to the CMB, basically a temperature map. And as you can see, the small scale resolution has been completely lost. but the large-scale information, the clustering on the very large scales that we need for cosmology is still there. So, and also a good thing is that the radio instruments just provide a fantastic redshift resolution. So you still have like a spectroscopic-like redshift evolution, but you have this low angular resolution map. So this idea basically has inspired many surveys that are currently ongoing or suggested. So one of them is a survey with the Green Bank telescope. I will talk about this later on. Another one is the Canadian instrument CHIME, which was made to do intensity mapping cosmology, but currently they are really good at detecting FRBs. They have a bunch of papers about that. So intensity mapping, the way it scans the sky is also very good for transients and FRBs, things like that. There is HIRAX, which is a dedicated, again, cosmology experiment with intensity mapping in South Africa. And then there's MeerKAT and the SKA, which were not originally built with cosmology in mind, but we want to do cosmology with them. And in fact, we are trying, we have data from MeerKAT and we are working on them at the moment. So what we can do with intensity mapping is basically get the maps and from them construct summary statistics like the 2-point function or the power spectrum. And it is very nice because we don't only do cosmology with them, but we can also constrain the neutral hydrogen, the H1 parameter, so the abundance and the bias of H1, which are things that are very important for understanding galaxy evolution. So also there are many galaxy evolution people who are interested in this technique, which I think is very nice. And you can see how we can do that. Basically, you can write an empirical model for the autocorrelation of H1 and the cross-correlation with a galaxy survey, and you see that the amplitude is proportional to the abundance and the bias of H1. So you can constrain them. And as I said before, you can also do cosmology. So one of the first papers that we really demonstrated the technique, and actually we suggested a purpose-built single-disk experiment to detect the baryon acoustic oscillations, was this paper in 2013, where basically we suggested this purpose-built instrument with the goal of getting rid of some systematics that we know that are problematic. And we showed, taking into account things like systematics, foreground, removal considerations, etc., we showed that in principle, it can measure the power spectrum competitively to the best optical galaxy surveys. So this a plot from that paper. Basically, we got like a 2% constraint on the BAO scale, which at the time was competitive with the state-of-the-art Wiggles and Bosch experiments. Of course, this was just a forecast, and there are many issues. As with every new method, there are quite a few issues. There is the foreground issue, which is similar to the problem that CMB experiments had, but it's a bit worse in our case. And also because it's a new method with new instruments, radio instruments, we have instrumental systematics we need to identify and control. So what many people, including myself, have been doing the last few years is that we have been turning our attention to working with Pathfinder experiments and trying to construct realistic simulations. Like the goal should be to construct end-to-end simulations, like optical surveys, did to reach the success they have now. I want to return a bit to the galaxy evolution. This is a plot I did for the SKA Cosmology Red Book. As I said before, H1 evolution is poorly constrained. It is very important for galaxy evolution. And this is basically, maybe this is a bit outdated now. There are 2-3 more points perhaps, but you can see that we do not have enough or precise enough constraints in a very wide redshift range for the abundance of H1. So from redshift range from 0 to 5, we would really like to populate this diagram with many more and better constraints and understand how galaxies evolve, basically. And with intensity mapping, if it works as we want it to work, this is very easy. We can very easily populate this diagram using meerkat, SKA mid or SKA low to reach the higher redshifts, and and really pin down galaxy evolution that way. So we can also use cross correlation with optical surveys to do so, and in fact we did that recently with data. This will be like my last slide. We can use cross-correlation with optical surveys, which massively helps because there are some survey-dependent systematics that just drop out in cross-correlation and really allow us to get constraints on omega H1, BH1. So on that front, we are doing quite well, I think, even with Pathfinder experiments. Now, one of the problems that we have that I'm very interested in, and many other people have worked on it, is that the 21 centimeter signal is very weak and the foregrounds are a big problem. So the foregrounds are orders of magnitude bigger than the signal. Depending on what redshift you are observing, they can be 3 to 5 orders of magnitude different. And the problem becomes even worse if you do epoch of ionization experiments, of course. So these foregrounds are galactic synchrotron, they're extragalactic point sources and free emission. And but fortunately for us, these foregrounds are smooth, non-Gaussian in frequency, which means that we can remove them and leave the signal as unaffected as possible. These are some simulations that my group has been doing. We worked with foreground removal methods, testing them in simulations and real data. So this is how synchrotron and point sources and free emission looks. They are really much higher in amplitude than the cosmological signal we want to recover. And this is an example of what we call a blind foreground cleaning. So blind methods work basically with principal component analysis. They separate what they see, the dirty map that they see, in different components. And the ones that are non-Gaussian in frequency, they are removed. But this comes at a cost. The cost is that we always get signal loss. You can see the difference between the black and the red line, which is the black is the true signal we aim to recover, and the red line is after we remove foregrounds in our simulations. So on the small scales, we are doing really well in this idealistic still situation because it doesn't have other systematics. But on the large scales, we do quite badly. We lose signal, and that is because there's a very simple reason for that, is because on the very large scales, the signal looks very similar to foregrounds. It's smooth in frequency, so it gets removed. So that is not necessarily a huge problem, but it means that you have either to correct for the signal loss somehow or model this effect and make sure that when you do parameter inference, you take this into account. And this is what we did. My student, Paula Suarez, led this project where we proposed to model the signal loss with 2 nuisance parameters. And we found that, first of all, it works, at least in our simulations. It works very well, and it is necessary to recover via Bayesian parameter inference procedure the true cosmology that we put in the simulations. So without it, we get very biased, wrong constraints. With it, we get the correct cosmology, and we also do quite well in constraining power. So in this analysis, we constrain the usual, if you like, parameters that optical surveys constrain. So the BAO, alpha parallel, alpha perpendicular, the growth of structure. We use a simple nonlinear modeling, so we have a few nuisance parameters there. The bias, etc. So on that front, I think there is progress to understand. Of course, ideally, we would like to remove foregrounds perfectly, but without having end-to-end simulations, that is very difficult. So now we are working on things like that. And last but not least, I would like to mention some data work. So the currently operating telescopes are the GB2 Green Bank telescope, which does many things plus intensity mapping. There is CHIME, again, that does many things plus intensity mapping. And there is Meerkat, for which we, in collaboration with the Meerkat team in South Africa, we had 2 successful proposals for observing time to do Pathfinder work with data and cross correlations with optical surveys. So the first thing I would like to mention is that the detections we have so far. So the first detection with GBT was led by Kiyo Masui and Tsu-Jing Chang in 2013. They had a detection cross-correlating intensity maps from the GBT with the Wiggles optical galaxy survey. And this showed that how important cross-correlations are because they mitigate systematic effects. In autocorrelation, we still don't have a detection. I should note that. After that, we had 2DF survey cross-parks intensity mapping detection 2 years ago. And we had the GPT EBOS detections this year, which is a work I co-led with Laura Waltz and Kiyo and Tsu-Jing. And from these detections, we can constrain the combination of omega H1 BH1. So we are starting to populate this galaxy evolution H1 abundance diagram that I was talking about. And this is a plot from our paper. So basically, we cross-correlated the GPT maps with Wiggles. So we wanted to reproduce the previous detection with an independent pipeline. And then we cross-correlated with EBOS ELG sample and the EBOS LRG sample. And we got detections in all cases at the level of 5 sigma. We used foreground removal with fast ICA, which is very similar to the simple principal component analysis. And we also tried to improve on the modeling and tried to make conservative forecasts using scale cuts, etc. So yeah, we were very excited about this work, and now we took these tools that we have developed for this work, and we are super excited to work with Meerkat data. So after years of forecasting and asking for observing time, we finally have observing time. We have science verification intensity mapping data at the redshift range 0 to 0.5, about 200 square degrees. We had a calibration paper out very recently, led by Jingying Wang from UWC in South Africa. And right now we are working on cross correlations with overlapping Wiggles galaxies. And this is just some maps, just to show you, this is work that my group is doing, just to show you that we simulate the foregrounds at some frequency, then we compare with the non-cleaned maps. They look, fortunately, quite similar, and we are currently working really hard on trying to do the foreground removal properly, comparing different techniques, and trying to do the cross-correlation with Wiggles. So keep an eye for hopefully many papers from Meerkat, and then the SKA coming soon. So that's it from me. Sorry, I went 2 minutes beyond time.
Oh, thank you very much, Alkisis, for a very nice talk. And actually, you were mostly on time. So if there is one question, maybe we have a short time for a question. You can also, of course, I remind all of you, you can raise your hand here. There is this option in Zoom. So I don't see any questions. So for sure, as I said, we have discussion we have time for discussion at the end of each section, this morning, later on this morning and tomorrow afternoon. So now, thank you again to the speaker, and I leave the floor to Elisabetta Lusso, talking about how AGNs can provide us clues on the accelerating universe. Thank you, Elisabetta.
Oh, thank you very much. So I'm going to just share my screen, which worked before. So you should see the first slide. Are you?
Yes,
okay.
Fine.
Thank you very much.
You.
So thank you, the organizer, for inviting me to this really interesting parallel session, and what I'm going to talk is a technique that we developed with my collaborator Guido Risaliti, University of Florence. Likely, the group is expanding. We are working with now many people now. Some of those people are actually attending this session, Lorenzo, Esther, so I'm very pleased to show a few very little new results on this project. So what I'm going to talk about is what quasars can tell us on the accelerating universe. And the first and foremost concept and question that one might ask is quasar a standardized volcano? So in order to do cosmology with quasars, this kind of astrophysical object must fulfill these two properties. It must be a source with a known luminosity, so we need to know their absolute value, and it should be easily observable up to very high distances. Regarding the latter, there is absolutely no problem because quasars can be observed up to very high redshift, and the current record order is now 7.5. One may argue that these kind of objects are actually very variable, and they are variable across the electromagnetic spectrum in the wavelength of light they produce. So how we can standardize their emission? So what we did was to use a relation between two different colors of quasars. One is at the X-rays and the other at the UV. And I'm gonna spend a little bit of time just to explain what the relation is. So this relation is not new. So we didn't discover any new relation, just to be fair. This relation was known since the 80s, is parameterized by the very much loved alpha Wex index, which is very well known within the X-ray community. It is an energy index that connects two portions of the spectral energy distribution of quasars. Namely, is the luminosity, rest frame luminosity at 2 keV, at the energy of 2 keV rest frame, and the UV luminosity at 2500 angstrom. The alpha Wex index was shown to get steeper and steeper as the UV luminosity increases, meaning that as soon as the quasar gets brighter and brighter in the UV, emits less and less X-rays. So this was observed by using several different surveys of quasars selected in many different ways. So there is no issue on that relation exists, and it is statistically significant. Yet the alpha Wex LUV relation is just the byproduct of what we consider the most fundamental relation, which is the one between the data, the two real values. So the X-ray luminosity and the UV luminosity. And this is what I'm gonna call throughout my talk. The slope is nonlinear, is 0.6, and this is a crucial point if we want to use it as a standard relation. And the main issue with this relation is the dispersion. So it was observed that the observed dispersion of this relation is, or was, I should say, quite high, on the order of 0.35x, if not higher. So with at the beginning with Guido Risaliti, we did a lot of work trying to understand the origin of the observed dispersion. We wanted to evaluate if the intrinsic dispersion is actually smaller, and if we can check that the slope of the relation doesn't actually evolve with time, then we are on business. So we can do cosmology with it. So we can use this relation not in a similar fashion as the Phillips relation for type 1a supernovae, but closely. All right, so these two introduce the relation we have been using, and now that we have the relation, we need to select the sample. And this is one of the main things that we stumble upon whilst doing this project of cosmology, because since light from the quasar has passed through many things, it is hard to recover the intrinsic emission. And by intrinsic emission, I mean the UV luminosity, and I should mention that there is also physics hidden in here. I don't have the time to talk about the physics behind this relation, but the UV luminosity is, as you know, emitted by the accretion disk onto the supermassive black hole, while the X-ray emission is thought to be emitted by plasma of hot relativistic electrons that content up scatters photons coming from the disk. And this is called the X-ray corona. Having that being said, light passes through dust and gas and gets absorbed, gets scattered. There are several kinds of quasars where additional physics is present, like, for example, radio bright sources, which can enhance the X-ray emission that we observe due to the presence of the jet. Or broad absorption like quasar, where the continuum, if you ever seen a spectrum of a broad absorption like quasar, is really hard to find the intrinsic continuum, which has been warped and distorted by the outflow that is present, or it is thought to be present in BAL. We need to take into account dust threatening. Here I'm showing just a list of possible things that we need to take into account, and that we call the selection criteria to select a clean sample of quasars. We have been working on this very much, and I should mention, I'm going to talk about this very, very briefly at the end of my talk, that we validate the selection criteria. We published recently a new quasar sample that is available to the community to use. So if you take into account all these systematics that I show here, or systematic contaminations and absorptions, last but not least is the Eddington bias, which is an evil beast, and we try to correct for the Eddington bias, and all the details are in the paper. So please have a look at the paper for the details. So here is one of our latest, is not the latest, relation between the X-ray luminosity as a function of the UV luminosity. The slope is very much the same as the one we knew already, so 0.6, but the dispersion is much smaller. So we are now on the order of 0.24 dex. We have been publishing and we are in the process of submitting papers where we can demonstrate that the slope can be even smaller. Just to show you that if you don't correct or take into account possible contaminants, this is what you get. Again, slope is the same. This doesn't change between uncertainties, but the dispersion is much higher. You can't do cosmology with it. We need to check if the slope does evolve with time, and you can do this with fluxes. So we did a regression analysis of the flux to flux relation, checking for the slope as a function of redshift, and we found that the slope doesn't evolve with time across the redshift range that we can probe. So we have a relation that is tight. I didn't have the time to talk about physics, but it's based on some physical grounds and doesn't evolve with time. So we can use it for cosmology. And here, I just want to summarize the main points of the technique. So it's true we start with luminosity, but what we want to do is work with fluxes, which are cosmologically independent. So we take out the luminosity distance value parameter, which is related to cosmology. And as you can see, since the slope is nonlinear, then I don't know if I can get the pointer here, maybe not. If the slope is nonlinear, then the luminosity distance doesn't cancel out. And therefore you can measure a distance in an independent way. And what you can have is a quasar, Hubble diagram, or a distance modulus redshift relation using quasars. This was our first Hubble diagram. I'm just showing this because it's since was our proof of concept. In this work, we first published the technique that we proposed. The Cyan points is a sample of type 1a supernova that back then, I don't remember, it was Union or JLA. It doesn't matter. You can see that the dispersion compared to quasars, which back then were just 800 sources, is much smaller for type 1a supernovae. Yet the red points represents averages of the distance modulus in narrow redshift bands, which are shown here just for visualization purposes. And you can see that there is an excellent agreement with supernovae in the common redshift range, which for us was reassuring. So we didn't do anything majestically wrong, but we can test the cosmological model in a redshift range that it is covered. This will be probed by any type 1a supernovae. And I want to emphasize even more what Michele just said at the beginning, that it is of paramount importance to use independent and different approaches to constrain the cosmological parameters even better. So here I'm showing the first, one of our first constraints on the dark matter, dark energy. These plots are customary in cosmology, but for us, it was just as a proof of concept that the technique works. So blue is quasars, open contours are 1 into sigma for type 1a supernovae, and red and orange is the combined. And the fact that quasars are complementary to type 1a supernovae is key. I should mention that we are not in the era of precision cosmology yet, but this is our goal and this is what we are working on at the moment. So we wanted to increase the sample, we want to improve the selection criteria, and a few years back we published a bigger sample where we included also some dedicated quasars, so a sample of quasar at redshift 3 with dedicated XMM Newton observation, for which we were awarded a large program, which are shown here with the blue stars. So, and cyan is, as I mentioned before, type 1a supernovae. So here I'm showing the best fit of the data below redshift 1.4 using a flat lambda CDM model. And I'm going to compare this fit with a cosmographic fit of the data using quasars plus supernovae across the entire redshift range. And as you can see, the best fit deviates from the model-dependent fit with a statistical significance that is above 3 sigma. So how to quantify this? We use, as I said, a cosmographic technique. Back then, we use a third-order polynomial expansion. There is going to be a dedicated talk on this by Esther, so I'm not gonna enter into much details. And we published very recently work on this. Giada Bargiacchi is a brilliant student. She is now doing the PhD at the Scuola Meridionale Superiore in Naples, and she just published all the details regarding the cosmographic technique that we employ. So please have a look at the paper. So I just want to briefly go through the main plot that quantifies this statistical, the significance of the fit, the cosmographic fit. As you know, if you can parallel the cosmography with any cosmology model that you like. So in this case, it's a third-order polynomial expansion. We use a flat lambda CDM, and this plane of the two coefficients, A2 and A3, a flat lambda CDM will look like this, with omega matter equal to 0.3 for a flat lambda CDM, which is highlighted here with the black dot. You can also employ a different model where we use a variable dark energy parameter. So this is the equation of state of dark energy. And as you can see, the curves are different. We'll probe different parts of this plane and just put the data on top. This is what we get. So if we fit the data using the cosmographic technique, using supernovae and quasar below redshift 1.4, this is what we get, as I said, fully consistent with the flat lambda CDM. If we include all the data beyond the redshift 1.4, the contours shift towards more negative W value. And as I said, if we want to interpret these contours within a WCDM model, this will suggest that the dark energy density will increase with time, as that lower corner is where the W gets more negative. But I should mention, this is within a model. Another way to show this, let's call it tension with the flat lambda CDM, is by comparing a full combination with supernovae, CMB, BAO with cleansing, and quasars, which is shown here by the 2 and 3 sigma with the flat lambda CDM again. The green contours is just CMB and BAO plus with cleansing. And as you can see again, the combined contours do show that there is a shift towards more negative values with respect to the flat lambda CDM model. Now that we know that there is this tension, we want to check whether there is anything we can pinpoint as a systematic or a bias. So we did a lot of independent tests, creating different samples of quasars by adding different kind of model-independent techniques. I'm just going to briefly go through, since my time is running out, I guess. So we did combined analysis using gamma ray burst. And this is what I'm going to briefly show. So we use one of the recent, probably there is a most recent data set now available of gamma ray burst. Here we just use, here you can see either both the redshift distribution and the Hubble diagram. And again, we can confirm that there is a deviation from the flat lambda CDM at the 3-4 sigma level. And this is also true for Pantheon and quasars. Is slightly less significant if we just use gamma ray burst alone with type 1a supernovae. But again, this is consistently seen in all the data set. We are also working with the students. The student is also working a lot by including also baryonic acoustic oscillations constraints on the analysis. And this is a work which is in progress. So these are new plots that we hope to get submitted very soon. And again, the point is the reference from the flat lambda CDM, and there is again some sort of consistencies or inconsistencies at the 3 sigma statistical level. The last, and then I'm done, is the new quasar sample for cosmology, which is available online. So please have a look, both at the paper, and if you want to use it, you are very welcome. And if you, the main point of this paper was to verify that the relation is redshift independent. We wanted to confirm that the tension is statistically significant, and we want to validate the selection criteria and all possible systematic and biases that we can think of. So I'm done, and I'm just going to leave you with the conclusions. Thank you very much.
Thank you very much, Elisabetta. Very nice talk. You were mostly on time, so thank you also for this. So if there are questions, please, from the audience. Massimo, I see, raised his hand. Massimo, you have a question?
Yes, yeah, I have a short question. Thank you for your nice talk. At a certain point at the beginning of your presentation, you were mentioning that there is an excellent agreement between supernovae redshift 0.3 up to Z1.4 with the quasar sample. This statement confused me a little bit, because I believe that you were using those supernovae to calibrate your quasar sample. Am I right, or I didn't probably I didn't understand your point.
No. That's right. I just probably I was too fast here. So it is true. So we do not measure absolute distances. So we need to do the cosmic ladder back. And in order to do that, we use supernovae to cross-calibrate, cross-normalize quasars and the quasar distance moduli, as you correctly stated. When I said that
sorry, so that's at this point we cannot claim that there is an agreement between supernovae and quasar. Is that right?
I was about to better say that when I say agreement, I'm talking about the shape. Since we are not, the shape doesn't get affected. So we are not changing the shape of the Hubble diagram in that redshift range. What we do is just the cross calibration. So the cross calibration affects the normalization of the distance modulus, but doesn't affect the shape. So the agreement that I'm talking and I'm referring to is the shape. I should be more precise here, is the shape of the Hubble diagram. So the Hubble diagram of quasar is very similar to the Hubble diagram of type 1a supernovae in the common redshift range. So this is what I refer, and this is what I meant when I say excellent agreement.
Okay. Thank you.
Hey.
Thank you so much.
Thank you very much, Elisabetta. Thank you again. Now we shift to the last talk of the first half of this session before the break. So Elisabetta, you can leave the screen to Luca Izzo, who is going to talk to us about cosmology with gamma ray burst. Thank you, Luca.
Thank you to you, Lorenzo, and the other organizer of this nice session. Can you see my screen?
Yes, now, yes, in full presentation mode, yes.
Perfect.
Thank you.
So thanks for the opportunity that you are giving me to discuss how gamma ray bursts can be used as cosmological proof, in particular as the standardizable distance indicator to trace the expansion history of the universe. Well, before going into the details of the technique, I think that a few minutes must be spent on explaining some properties of GRBs. Well, you know, there are quick flashes of high energy radiation initially observed in gamma rays, where their temporal emission, also called the prompt emission of GRB, is quite diversified. But as time goes on, sorry for the noise, background noise, as time goes on, the bulk of the radiation shifts from gamma rays to lower frequencies such as X-ray, optical, and also in radio. And in particular in X-rays, we can observe that the so-called afterglow emission component can be categorized in few subclasses. On the other hand, the energy distribution of the photons emitted during the prompt emission can be successfully modeled using a phenomenological function also called the band model. The band model is best described as a two power law, one at low energy and the other one at higher energy. It's mutually connected at a given energy value, also called the peak energy of the prompt emission. Another important property of gamma ray bursts is that they can be classified in two families based on their intrinsic duration of the prompt emission, namely short and long events. And this classification is not only temporal, not based on the temporal, sorry, observation duration distribution, but it is also reflected in the spectral of the prompt emission, with short events being more harder, so with peak energy much higher than their long brother. So, and also this classification is also physically connected to the progenitor of these events, with short events very well known to be associated with the merging of two compact neutron star, while long events forms from the collapse of highly rotating massive stars. And in both cases, we have the formation of a central black hole or a magnetar that can produce a highly relativistic collimated jet that is responsible for the duration of GRB. Well, so GRBs, according to their flux observed, are very energetic and luminous events. And this evidence also has permitted us to observe these events at very far redshift. The most distant event has been observed almost 12 years ago at a redshift of 9.2, and the redshift is mainly determined with the spectroscopic observation of their optical afterglow emission. So redshift 9.2 means almost a few hundred million years after the Big Bang, well inside the epoch of the reionization when the first galaxy began to form. Consequently, it seems very natural to search for a way to render gamma ray burst as a standardizable distance indicator. And the only possible method consists in using correlation between observed photometric and spectroscopic property of gamma ray burst, with one of these two properties being dependent on the cosmology and other one or more being independent on cosmology. I will show an example with one of these correlation very soon. Just want to say that GRB can be observed in a very wide, probably the widest redshift range for any single astrophysical source, and more important, they are not affected, in particular for their high energy emission, by dust extinction problem. This is one problem that affects many secondary and primary distance indicators, such as also type 1a supernova. Just to mention that the fact that GRBs can be observed very high redshift render them very useful to search for possible extension of the lambda CDM mode, in particular for the evolution of the dark energy equation of state. But given that the dark energy component is not the dominant one at redshift larger than 0.5, we really need very accurate distance indicator at this redshift. Oh, sorry, okay. Okay, so one of the most promising and tested GRB correlation is the EPK isocorrelation, also known as hour chair relation, Amati relation. And this correlation connects the intrinsic peak energy of the prompt emission set in long gamma ray burst and their isotropic energy emitted within the same time interval. And well, I already mentioned this correlation is satisfied only by long gamma ray bursts, and it almost span almost 6 orders of magnitude in energy. In the detail, just to display the concept that I mentioned before about GRB as standardizable candle, the peak energy is our independent, cosmology independent observable, while EISO is, let's call our candle. EISO is related to the cosmology, the luminosity represented by the luminosity distance, through the observable bolometric fluence. And the bolometric fluence can be inferred with, by the integrated flux modeled by the prompt GRB spectrum. And once we derive the luminosity distance inverting this correlation, we can build the GRB Hubble diagram and then make all the tests we want on cosmological model. And indeed, the use of the Amati relation has provided for the first time an estimate of the cosmological parameter at high redshift with GRB, with very interesting result if compared with other non-standard probes. Here I also want to mention an interesting characteristic of the scatter of GRBs obtained using the Amati relation. If we want to compare with the Pantheon sample, where the Pantheon sample is composed by many samples, but if we consider only the photometrically classified supernova, that includes also core collapse supernova that are not really 1A, the scatter is very similar, if not the same. Well, for more details on the Amati relation, I strongly suggest to see the talk of Lorenzo in one of the plenary. Sorry, I don't remember exactly the day. I will check the program later on. Another interesting test that has been done with the Amati relation is almost it's also independent on the calibration actually of the correlation. So assuming assuming that the Amati correlation is real, is valid for all long GRBs, in principle we can vary the underlying cosmology and check what is the best set of parameters that render the scatter of this correlation as much lower as possible. And this has been done in a paper by Lorenzo and Della Valle in 2013, and they got interesting results very in agreement very well with primary standard in distance indicator. Okay, so we have still some time. Just to say that in the last 15 years, other correlation between GRB observable properties have been proposed and the majority of them have been also described in several review papers. I suggest the paper by Dainotti et al. In 2016. But here, I want to spend some time show you some interesting results that we have obtained using the combo relation, which is a new relation proposed a few years ago that is named combo because it's the combination of the EPK isorelation with its extension to the X-ray isotropic energy. And well, this is the final results. I'm going into the detail now. Actually, the key point is the X-ray emission. As we have seen before, the X-ray emission can be categorized in a few subclasses, but can be modeled by a single phenomenological function proposed by Willingel in 2008. This phenomenological function modeled very well the early decay from the of the X-ray afterglow, also sometimes also called the high curvature emission from GRBs, and the second component, the plateau X-ray emission, just using three parameters: the plateau luminosity, the time constant tau that marks the beginning of the late decay, and the decay index alpha. Actually, we have implemented a light curve fitting procedure for using this phenomenological function for X-ray afterglow, very well similar to what is usually done for type 1a supernova, with the additional advantage that, okay, X-ray emission is very less affected by extinctions, as type 1a supernova can be also inferred directly from the X-ray spectrum, the extinction. And in particular, we have implemented an iterative algorithm that get rid of X-ray flare overimposed on the X-ray light curve. So actually, the final result is a two-parameter relation characterized by a small data scatter. And unlike other proposed method, GRB correlation, it does not contain outliers. So, I mean, all GRBs for which we can measure these parameters satisfy this correlation. And we have also proposed a two-step calibration, one of the big problems of GRB correlation that is based on, well, to calibrate the two main parameters of the correlation, the slope and the 0 point. For the slope, we have considered different mini sample of GRB at same redshift so that we can get rid of the cosmology and use the flux for the fluence, actually, not the flux. And we have estimated, we have not only estimated the slope parameter, but we have also verified that this correlation does not vary with redshift. While for the 0 point, we still need to rely on type 1a supernova because the nearest GRB was observed at redshift 0.14, which is still a bit higher for distance measure using direct distance indicator, primary distance indicator, sorry. And we used, well, type 1a supernova for this normalization. And the candle here, as mentioned before, is the plateau luminosity. And using this approach, similar to what has been proposed for the mitigation before, we got some very interesting results, also using a relatively limited 150 sample of GRBs. And recently, Muccino, using an updated version of the sample, has also put some constraint on the dark energy evolution, dark energy equation of state evolution, using a piecewise method for the approximation of the luminosity distance. So far, so good. But now, I think it's mandatory to discuss the main problem that affect the use of GRB as a standardizable candle. The lack of GRB at very low redshift indeed prevents us to use primary distance indicator, I mean, Cepheids, SBF, or other direct standard candle. And indeed, the most nearby event, the only very nearby event, 980425, does not have a great coverage in X-rays, and also its intrinsic properties of gamma ray emission well, do not assure that we have really observed a jet, but this is another story. This led some authors to use alternative techniques based on assumption of underlying cosmology, or to use approximation for the distance formulation that, however, are affected by artificial approximation for the luminosity distance, in particular at high redshift, because we need to cut these high order series at a certain order, and we do not have a complete criteria. I think that Esther will discuss this thing in her talk after the break. Actually, there are other methods, Massimo mentioned before, the fact that high redshift distance indicators are generally calibrated with type 1a supernova, but of course, this method is a 7-step calibration procedure, because the supernova array is already a 6-step calibration procedure. And more important, since, as Michael mentioned before, we want an independent probe, independent distance indicator, using type 1a supernova implies that we are, let's say, that the cosmology infer using high redshift or no standard probe are biased by the cosmology that has been inferred using type 1a supernova. Selection effect also affect the final likelihood function, but they are actually rarely taken into account for almost standard probe. In addition to the fact that within a single GRB sample, we can have GRBs observed with different detectors, with different energy range, different response matrices, and so on, it's also very likely that for moderately high redshift events, sorry, we will only not observe, take into account bright bars, because mentioned before, we measure the redshift for afterglow that are bright, but there are almost more than half of GRB for which we cannot identify an optical afterglow. We cannot measure the redshift, and maybe they have different properties. And finally, and want to spend a few time on this because it's something that is very interesting for about and was used recently used in several approaches. I mean, the use of machine learning algorithms to trace the luminosity distance function for the calibration of GRB correlation. I think that this approach is very powerful and interesting, but it is also affected by the correct use of their correlated uncertainties. Generally, in a machine learning approach, there are many sources of uncertainties, such as variance and covariance of the data. Each single GRB affects the value of omega and and also the cosmological parameter, in addition to the systematics that have never been discussed so far in the literature. Generally, these uncertainties are managed using probability theory, and this implies the development of advanced models. Mainly for machine learning approach, we should use Bayesian network approaches. But the main source of uncertainty comes from noisy data. Actually, there is a trend nowadays to use these galaxy ages, which, however, have been recently demonstrated to be affected by large uncertainties, in some cases also of the order of 100% on their agency value. This implies completely wrong posterior distribution for any GRB correlation parameters inferred using this method. And then I want to suggest that great attention must be taken when incorporating prior distance information for the calibration of GRB correlation. So, okay, this is my conclusion. I think I'm in time also for some questions. Well, I think my conclusion is that GRB are a very powerful tool to investigate the high redshift universe, but we still miss a complete treatment of their uncertainties. And more important, we also are still missing a completely unbiased calibration technique and sample as well. Okay, I think I'm...
Yeah, thank you. Thank you very much, Luca. Thank you for the very nice talk and for being perfectly on time. So as you say, there is time for questions. So please, if any colleague in the audience has some question for Luca. Clearly, Luca had to go very quick, but there are, as for previous talk, there are many critical aspects on this very promising field. All the three fields that have been described up to now are actually potentially very interesting for cosmology, and from going beyond, of course, the results can be achieved with current, let's say, standard probes, of course. So, Luca, I just ask a quick question to you. Is there any way or hope to use this correlation for gamma ray burst, or these methods for gamma ray burst, for investigating the H0 issue?
That's a nice question. Actually, you know, H0 is the actual expansion rate of the universe. In principle, we can use GRB for H0, but the related uncertainties will be much higher. So in the plot that Michele showed about all the different values of H0, probably the error bar obtained using GRB will be much higher. In the case of the Marco-Muccino analysis, for example, we have marginalized the H naught value using the, well, we made two different analyses using the Planck and the supernova 1A recent at the epoch value, most updated value. But in principle, you can also let the H naught to vary. We didn't do this approach because we had the nearest GRB at 0.14. The entire CSP sample of type 1A supernova, the DR3 or the foundation, is at lower redshift. So in my opinion, it doesn't make sense to use GRBS at the moment as estimator of H naught. Okay,
so here a relevant contribution may come instead from short gamma ray burst and
definitely
with gravitational wave signals, no? That instead.
Yeah, but I think this is something that will be discussed in the next session by using standard method.
Yeah, of course. It's one of the many potentialities of gamma ray burst, no? Okay, so thank you very much, Luca. So let's take, I would say we can take 10 minutes break and reconvene at 5 to 11, so 10:55, and then the session will be chaired by Massimo Della Valle. Thank you very much again to all the speakers, and let's get in touch in 10 minutes. Thank you.
Think we can start again the second part.
Sì, ciao.
Do you want to go, Massimo?
Yes, I'm here. Can you hear me? Yeah, I guess so. Yeah.
Yes.
Okay, let's start with the Esther Piedipalumbo. She would talk about the cosmography, the renaissance of cosmography. I'm very curious to hear your talk. Please, start it.
Okay. Can you look my, okay. Is it possible to look at my presentation?
Yes,
okay.
Go ahead, please.
Okay. First of all, good morning to everybody. I thanks a lot the organizers for this possibility they offer me. This talk I will try to discuss the possibility open from non-standard cosmological probes for cosmography. Cosmography is a, let us say, old-date approach to cosmology, but which is experiencing a real renaissance in the last 5 years, more or less. The main, the heart, we could say the heart of cosmography is that it is a kinematic approach to the cosmological evolution, which is important because offer the possibility to test a wide class of cosmological scenario on simple base of the cosmological principle, just assuming that the universe can be described by the Friedmann-Lemaitre-Robson-Walker metric. And of course, this is very important when we face our poor knowledge on the nature of the components of the universe, mainly, for instance, the dark energy. From the practical point of view, the cosmographic approach is based on a tailored expansion on the main cosmological quantities, starting, of course, from the scale factor. It is a quite old approach to cosmology. Actually, at the beginning of the 70s, Sandage, in a very famous paper, defined cosmology as search for two numbers, Q, the Hubble constant, and Q0, the deceleration parameter. Of course, at that time, this was in a sense simple, because the available data were in a sense limited to the low range of the redshift, and the cosmological scenario was simpler. But the situation deeply changed at the end of the last century, when started the dark energy cosmology in connection with the accelerated universe. Well, and of course now it is not possible to stop the cosmographic series at so low order. Actually, is needed to go much to much higher than. Actually, for instance, we here we look the expansion of a scale factor at 5 order, and of course this implies that we have to introduce new cosmographic parameter. That is not only the Hubble constant or the deceleration parameter, but also the so-called jerk parameter, the SNAP, and the so-called LERC parameter. It is worth noting that the jerk parameter in particular is quite interesting parameter, because if its value is equal 1, exactly equal 1, it corresponds to the lambda CDM model. So it's in a sense very interesting cosmographic parameter. It's also important to note that, well, 5-6 years ago, Saini and Starobisky developed a sort of simplified version of the cosmography, which is based on the so-called state finders parameter, but this is another story, just for completeness. Now, in a completely equivalent way, we can start not only from series in time of the for instance, Hubble, the scale factor, but we can start with the redshift series, Taylor series of the Hubble function. Here we look at the 3-order Taylor expansion of the H function, and of course we see the combination of the cosmographic parameters which appears in this series. What is very interesting to note, very important to note, is that not all the cosmographic parameters are independent, as in a sense we can look here, because if we want, for instance, consider an nth order series, Taylor series, we will find that only n-1 cosmographic parameters are independent. For this reason, actually the Hubble constant is not always considered a proper cosmographic parameter. Anyway, but it's also possible to obtain expression in terms of the cosmographic parameters of, for instance, the scalar curvature R, basing this is the definition, this is the connection with Q, and of course we can derive this representation, obtaining these two relations, which are, for instance, very interesting if we would be interested in testing, for instance, FR order theory of gravities, because of course if we can imagine to compare the cosmographic series which hold in not only in any cosmological model but also in any cosmological theory, based, for instance, on FOR gravity or FOT gravities. Now, this model with torsion are very popular. And to do this, we need, for instance, a relation like this. But from the, of course, our main interest is, in a sense, in comparing there's theoretical expression with some proper data set. So, of course, we have to construct the cosmographic Taylor series for some observable quantities. Here we show the expansion of the luminosity distance. This is a 5-order expansion, and this is a 4-order expansion of the H factor. Okay, if we have the Taylor expansion of the luminosity distance, we can, of course, very easily construct the modulus of distance with this simple relation. Okay, but this is just an example. We could construct the the cosmographic series for the angular diameter distance or for the volume distance. And of course, this implies that we could construct the cosmographic series, for instance, for using data set from Zeldovich or from the BAOS, or for instance, it can be interesting to construct the Taylor expansion in terms of the cosmographic parameter of the combination of the angular diameter distance appearing, for instance, in gravitational lensing, as for instance in time delays or in the Einstein radius. Just the techniques is the same. This is just an example. Of course, so and what is very interesting is that this series hold in any cosmological model and in any theory of gravities. But of course, there are also some drawbacks. Okay, the main drawbacks of this cosmographic approach, this is the standard cosmographic approach, the more traditional cosmographic approach, of course, have to do with the fact that we have series which are constructed close to z equal to 0, but we know that most of our data lie nowadays much outside this range of redshift. So it could appear a sort of unrealistic approach to use the cosmography to explore the high redshift universe. But it is possible to face this problem in different ways. The simplest way was the one to introduce new redshift. For instance, here we see the first historical proposed auxiliary variable epsilon redshift, which is very simply related to Z. It is not the only possibility. This is simply the first and, in a sense, the most popular. From the point of view of the mathematical properties, we can say that the convergent radius is the same, but the series remain in the convergence range also up to the relic radiation redshift, okay? And of course, this is quite important because epsilon, for what on the basis of its own definition, map the zero infinity interval of the redshift in the limited 0-1 interval. So, in a sense, it's convenient. For instance, in this plot, we compare the real, the exact modulus of distance for the lambda CDM model and the cosmographic approximation with a series extended at 5 order in the epsilon redshift. Here we look at the relative error, and as it's in a sense obvious, we see that the precision of this, the accuracy of this approximation works quite well at lower values of the epsilon redshift, but remain at the end reasonable values. This is actually the series in the epsilon redshift, which correspond to this modulus of distance. Okay. Of course, using the some auxiliary variable as epsilon redshift is a possibility, but it's not the only way, because not only because some convergence problem can remain, but for instance, we will return back on this in a few minutes, if we want to approximate the Hubble function, which is in a sense the most delicate observable quantities, but also because there are some degeneracy. A very important it's very important to note that the series which we show are a series related to a flat universe. So when omega k is exactly 0, but if omega k should not be set equal to 0, we will say some degeneracy among cosmographic parameters and the omega k, and of course this is a problem in itself. For this and other reason, in the last years, cosmography evolved in a sense, and some new approach have been proposed. One of the most interesting is based on the so-called Padé polynomials, also called Padé approximant. Of course, the idea of the Padé approximant is very old, and is based on the idea to use not a series, a Taylor series, to approximate a function, but to use a rational function. But of course, we are interested in the Padé approximant for cosmological quantity. The way the procedure is
Esther, sorry, just to tell you, 5 minutes to go.
Okay. Yes, thank you very much. Okay, the techniques to fix the parameter of the approximant is, in a sense, is very simple. It's based on match the terms of equal power. And at the end, we can see some approximations, Padé approximant, for the luminosity distance. Of course, depending on the values of the m of n, we have different possibility. Well, it's turned out that one of the most interesting approximant is the 2-1 Padé approximant, and actually, in a sense, because it's the best performing approximation, we look at what's happened with this approximant here. Again, we construct the comparison between the exact luminosity modulus of distance and the Padé approximant, and this is the relative error. We see that, of course, we are, in a sense, reducing accuracy, but we are gaining very important things. We have just two parameters, Q0 and J0. So, in a sense, this is very important. Of course, we can do the same for instance, Hubble function. We can, for instance, obtain the Padé Q1 Padé approximant for the Hubble rate, starting from the third order series for the same function. And this is the comparison between the exact function and the relative and the Padé approximant. Well, I have just said a few minutes ago, we look, of course, at one of the main aspects of the using H, because, of course, the H function, double rate, is the most delicate function to approximate. Here we are plotting the relative error in order. So in our analysis, we want to show data result with which you use also measurement of the Hubble function in order to keep the accuracy at a good level, let us say around 1%. We will limit our data set in this range. So what are our observable? Well, from a point of view, we will use Hubble diagram dataset. We will use gamma ray bars Hubble diagram built up with the epic ISO relation, with the Amati relation. I'm very lucky because Luca talk was previous than mine, so I can skip this part. And also the quasar Hubble diagram shown by Beta few times ago. Okay, here some few things about the gamma ray bars. We are using the epic ISO correlation. In calibrating this correlation, we include also some terms which, in a sense, offer the possibility to take into account possibly evolutionary effect. If we fit the calibration, fit the correlation, of course, we can construct the luminosity distance, which is, in our case, of course, depend on the parameters of cosmographic parameters. In our case, it depends, since we are using the Padé approximant, on Q0 and J0, the deceleration and the jet parameter. Okay. Well, we use the Ricard likelihood to fit our correlation. And as technique of calibration, we want just to say a few things. Yes, it's from a point of view, we can use the luminosity, the distance as built up by supernovae. So we can use supernovae to calibrate the Hubble, the epic ISO correlation, but we did the same using a very different approach, that is putting all the parameters, cosmographic parameter and the correlation parameter in a Wool likelihood. And here in this plot, we see the comparison of the two calibration. So we are, in a sense, confident that also using supernovae to calibrate the epic ISO correlation of long gamma ray bars is not a source of so big biases, let us say. Here we see the result of our fit. This is the cosmography, the best fit cosmographic values. And the line, the black line, the green plot points are the gamma ray bar Hubble diagram. This is the supernova data set, and Epsilon is the Epsilon redshift. Okay, this is the Hubble diagram built up using quasar, as explained by Beta a few times ago, so we can go. And this is another data set, the data set of H-zeta measurement with built up with cosmic chronometers. We will see the Michele talking a few times. This is the full data set we got, constructed mainly from these two reference, but in order to limit to have a good accuracy in our approximation with the Padé approximant of the H, we limit the data set, strongly limited the data set, as we see. Okay, Now, what are the results for our statistical analysis? We build up a standard likelihood. We sample the space parameter running 5 Monte Carlo chains, and we use the Gelman-Rubin diagnostic to test the convergence. And these histograms of the parameters for the matter chains have been used to obtain the best fit and the regions of confidence. Here we look, in a sense, at the most important plot, the two-dimensional confidence region in the Q0, J0 plane, which is the only plane of our cosmographic approach, because we are using the Padé approximant. And we see that the value 1, which is the values for the jerk, which correspond to the pure lambda CD model, is off at more than 3 sigma, according to our analysis, based on quasar, gamma ray bars, and H-zeta measurement. Here we see the plot of the best fit curves and the dataset in itself.
Esther, you are 5 minutes off. Sorry.
Okay.
You should
so
go straight to the conclusion.
Okay.
Thank you.
So just to say that there are new possibilities, a lot of fun with cosmography. For instance, we could start not from Padé approximant of the luminosity distance of the H factor. We could start from Padé or generalize Padé approximant for the Q zeta, and we obtain in a sense exact even in terms of a geometric function for the luminosity distance. And in a sense, we have again the same result for the jerk. So at the end, cosmography, even if an old date approach to cosmology is yet a challenging rope to investigating cosmological model in a lot of cosmological scenarios. And moreover, joining high redshift new probes, as for instance gamma ray bars or quasar Hubble diagrams and able H-zeta measurement, will increase the possibility to test this approach, the cosmographic approach in itself, but also to investigate to more details the nature of dark energy. Thanks a lot for your kind thanks.
Okay, thank you, Esther. When we don't have time for questions, and we can take questions on the Esther talk at the end during the discussion, and we move to the next speaker, that is Michele Cantiello, and he will talk about the impact of surface brightness methodology on cosmology.
Okay, do you see my screen, right?
Yes, Michele, I will warn you when you have with 5 minutes left. Okay?
You don't have to, but okay, that's fine. I hope you don't have to. So first of all, good morning, everybody. I'd like to thank the organizers of this nice parallel session, and I also like to acknowledge the collaborators of about this research line on surface brightness fluctuation studies, which is now about 20 years old here at the Observatory of Abruzzo in Teramo. So this is the outline of my presentation. I'm going to show why SPF play a role in physics of gravity, and then why we are here at MG16. I will spend some time on definitions and property of this technique, and then say some words on the present of cosmology with SPF and the future, and then go to my conclusions. So first of all, okay, here, this is a distance indicator, which is kind of different from what we heard up to now because it works in a redshift regime, which is a couple of orders of magnitude smaller than the other probes that we have here, like GRBs or quasars. As the outermost distance reached up to now is of the order of zeta less or equal 0.04. Yet it plays a key role in many studies of in astronomy and also in gravity. You have seen these you see these three images in this view graph, and you probably either recognize these three objects. One of them, I think there is a session. No, yeah, there is a parallel session dedicated to it. So these are NGC 1052, which is the supposedly dark matter-less ultra-faint dwarf galaxy. Then there's NGC 4993, which is the host of the first gravitational wave with electromagnetic counterpart. And then there is the image of the supermassive black hole in M87. So all three objects have a lot to do with gravity, dark matter, black hole, or gravitational waves. In all three cases, the point in common with SPF is that they're most accurate, or their only distance up to a certain time or up to now comes from the surface brightness fluctuation method. So let me give you a very brief outline of the qualitative idea of how this technique works. So this distance indicator works, as I said, out to a relatively low redshift regime to the one presented up to now. The basic idea is qualitatively very simple. We measure surface brightness fluctuations, SPF, for objects whose light is dominated by the emission of stars. Here you see two examples, mostly old stars. M32 at 1 megaparsec, you see how the image look like, and then another object of the same morphology almost, but 100 times farther away. You see that in one case, I think you see, I hope you see my cursor, the image is very granulous, very mottled. In the other one, the image looks much smoother. So if you have a quantity, so if you define a way to quantify this granulosity, you have a quantity that correlates with distance. So the basic qualitative idea of SPF is that you need, we identify the way to measure such granulosity. The first work to to define such a quantity in a modern way was by Tony Schneider in 1988. Basically, they quantified this fluctuation via the ratio of the second to the first moment of the stellar luminosity function in the observed population. Now, this is the theoretical definition. How do we go to distance modulus? Well, once you have the apparent measurement of the SPF, you need a calibration. That's another important point. Then you get the distance modulus, and from there you get, as usual, like all normally local distance indicators, you get the distance to the object. How do we get, first of all, to the apparent SPF? Well, that's a lengthy process. I don't want to go to the details. We may discuss it later, maybe, but I want to highlight a few points because this is important to show also the limitations and then later the strength of this method. So we have the galaxy image, we model the galaxy, we subtract it, then it's normalized somehow, and all the sources that you probably see in this image need to be masked out because they generate extra fluctuation. Then we finally have a masked fluctuation frame. Since the SPF signal is convolved with instrumental PSF, we go to the Fourier domain to deconvolve the signal, and then we get the amplitude of fluctuations here indicated as P0, and then finally we get the apparent SPF amplitude and extract it as usual in astronomy. Now, there is a small detail which is important, but I don't want to go too much deep in that, on that. It's we masked the sources, obviously, but there are still sources that contribute to fluctuations, and we don't see that because they are beyond our completeness limits. So we need to estimate this quantity, P sub bar, which is the spurious fluctuation term, and need to subtract it. This P sub bar is basically what sets the outer distance that we can reach with SPF. Obviously, as I said, once we measured the upper end SPF, we need a calibration to get the distance modulus. Now, in a survey in around 2000, Tori and collaborators with a Herculean effort, they measured SPF in 300 galaxies and derived the calibration from galaxies in the same groups. So by setting the 0 point using CFITs, they derived this equation that gives you the absolute SPF versus the galaxy color, which is obviously something that a quantity that does not relate on, does not depend on distance. So once we have a combination of the upper end SPF and the calibration, you straightforwardly go to the distance modulus. This is with empirical calibration. One big advantage with this technique compared to other methods is that we can calibrate it theoretically using numerical synthesis stellar population models. So instead of, like for other distance indicators like supernovae, for which the present calibrations can only be empirically based, at least the most reliable ones, here we can theoretically calibrate this distance indicator. There are some pros and some cons, but anyways, this is one of the advantages of this technique, that we know perfectly well where the signal comes from. And it's, as I said, mostly the magnitude of RGB stars. This is my last slide on the definition of the technique to give you an idea of something that has been discussed up to now in a different ways with the other cosmological probes. So there are very naively two sources of, the two sources of uncertainty, systematic and statistical. The systematic error here is only due to the 0 point calibration. So to the tie of the distance indicator to the primary distance used for calibrating it. To date, this systematic effect amount gives a contribution of about 5% on single distance, on a single target. Actually, recently, Blakeslee and collaborators published a paper, and they did something more refined, and they got an uncertainty of the order of 4%. So a systematic contribution. In the future, with the combination in Gaia and JWST plus TRGB studies, we expect to reach to get a systematic uncertainty much better, much lower than 2.5%. The statistical errors, so there is a combination of them here listed, a few of them main contributors to the statistical error. But in well-designed observations, you can keep the statistical uncertainty well below 5%, actually to the order of 3% on single target again. So by the end of the day, that's the take-home message, with this distance indicator, we can get a distance on a single target with an accuracy, global accuracy, combining systematic and statistical error of the order of 5%. Now, I know there will be discussion also this afternoon probably on this, the so-called tension on H0 from the local and primordial H0 values, and something that Michele this morning introduced in his presentation. Here there's an historical collection of H0 values with HST, but here I want to focus the two most recent ones, actually, with the two which also Michele presented in his work based on SPF. There is this Ketan et al. 2021, which actually is, I am a collaborator of that work, and it's a bit less precise than the other more recent one, because it's basically, it collects inhomogeneous data, and because of that, it has large uncertainties, large systematic and statistical uncertainties, and it basically agrees with both the Planck and the the supernovae H0 values, as also shown by Michele. But the most recent and more accurate homogeneous value obtained by Blakesley and collaborators, and I'm not in that paper, it's basically confirmed with a very low statistical uncertainty, and the H0 values from the supernovae. Note that it is derived from a completely independent road with respect to the supernovae roadmap, while the Ketan result depends on supernovae. So here, with a completely independent approach, Blakesley basically obtained a result which agrees within 1 sigma with the supernovae and disagrees within 5 sigma with the primordial H0 values. So this is the present, and what's next? What is the future we expect? So with this technique, as I said, we cannot go much far, but with the future, with the wide and deep surveys, wide with the Rubin Observatory and Euclid, and deep with James Webb, BLT, and Roman, things will probably change. Let me go first on the 2 survey telescopes. So going wide, we expect that by combining the data set of Rubin and Euclid, we will get observations of the sky of maybe a fraction larger than 70% of the sky. And with the I band for LSST and H band in the case of Euclid, we could get distances to any galaxy at a distance of the order of 70 megaparsec for LSST. LSST is the legacy survey of space and time from Rubin. And we will get probably out to 100 megaparsec with Euclid, probably even more for the brightest and most massive galaxies. What does it mean? It means that we'd have probably a number of targets that is something of the order of hundreds of thousands of galaxies, both massive and less massive, for which we could measure surface brightness fluctuations. And in this sense, we could get accurate distance with uncertainty up to a level of 5% for a huge number of objects. This is a great opportunity, clearly, but it's also a big challenge. That's why I've shown you how we measure SPF, because measuring this signal, it's not really a straightforward process. It takes a kind of a long time. And now we are working with our PhD student, trying to get some procedure that does it in very in a fast and reliable way. Clearly, once we will get these hundreds of thousands of distances, we will have accurate distances, and at the same time, some distances are also important to accurately map the cosmic flows and velocity distribution. And when you do H0 estimates from the local volume, you clearly need to correct for peculiar velocities. So we expect that with the combination of the data from these 2 massive surveys, we will get really accurate H0 values from the local universe. But then with James Webb, BLT, and Roman telescope, things will change also in terms of the depth we can go. To date, we reach distance of the order of hundreds of megaparsec with either HST or 10-meter class telescopes. But what we expect is that thanks to the higher resolution, for example, with ELT, that it's going to reach 5 times better resolution than HST, or thanks to much larger collecting area, more efficient imagers, and also thanks to the fact that these instruments will observe in the near infrared, we expect that it is possible that SPF distances will get to a distance regime of the order to a Z value of the order of 0.1 to 0.4. So this is the present status. Here I borrowed this slide from the supernova faults. Here you see, this is the present status. And clearly at present, the green bar represents the present distance regime with with SPF clearly. And this distance regime, you don't see cosmological effects. at least not at the precision that we have. The thing will change with these future telescopes, where we probably could reach with lots of problems, obviously. There are lots of details which I didn't mention. But for example, for the ELT, one of the main issues going to be the modeling of the PSF. By the way, if we manage to have a few targets with the well-defined science cases, we can reach this distance limit, where at the accuracy that we predict to have with the SPF, these are crosses, I put them randomly, and the error bars are estimated there about twice what we expect, so what we see, we foresee is that with SPF in the with the future telescope, this future ground and space telescope, we can get direct distances to a distance regime, a redshift regime, where we can constrain cosmological models. It's going to be hard, obviously, but it's feasible, and you will get something that is completely independent from supernovae and also from CFIS. So there is a possible independent roadmap to cosmology. As promised, I'll be on time. These are my conclusions. A few things, but I want to highlight here something that I want to probably later we can discuss. This indicator, besides the other properties which I discussed, can be also, and this is a question mark actually, it can be used to calibrate also distance indicators that go in a larger redshift regime, like something that has been discussed this morning by Luca, for example, the GRBs. So I hope I didn't go too fast, and thanks.
Okay, thank you very much, Michele. Indeed, you were in time. A couple of minutes. You save a couple of minutes. So, there are any questions? Okay, Michele, go ahead.
Yes. Thank you for the presentation. It was really, really good presentation. I have a question about your when you showed the determination of the Hubble constant. Because from the table that you were, yeah, exactly this, it seems that the results are pretty stable with time. I was wondering, playing a little bit the devil's advocate, are there any systematic effect that can shift the Hubble constant value towards lower values? So because this seems really similar to the results obtained by Shoes or similar.
Okay, I'm still. Do I have my microphone here? Yeah. Do you hear me, right? Okay, so actually, as I said, the only systematic effect, okay, you see here the estimate of the systematic error from the various in the various works. Actually, there was at some point an estimate of the order on H0 of the order of 80. Except for the calibration issues, the 0-point value coming from CFITs, and that might be an important systematic, there shouldn't be anything else. Also, the work by Blakesley, the recent work by Blakesley, what it did is actually, you know, that in order to get accurate H0, you don't only, you need accurate distance, but you also need the accurate velocities, and you know, and correct for peculiar velocities. And they have done a great job in collecting data from different cosmic flow models, and basically they ended up with this H0 and this uncertainty. But this is something that adds more scatter should add sorry, some systematic. As far as we have done our study, there's nothing else besides that, besides the 0-point calibration. There's nothing else. I'm thinking that oh yeah, as I said, there is the calibration from CFIDs, so that which is probably a big no, not that big, but certainly a significant problem, because CFIDs are measured in galaxies which normally host young stars, and so in spirals. Here, instead, we are talking about the distance indicator that relies on old stars. This might be a systematic effect, but there have been a couple of attempts. One from Mould and I think it's this one, Mould and Sakai, and yeah, it's in my notes. This is a TRGB calibration, but a more recent work from Blakesley based on TRGB, more modern TRGB estimates, which basically reduced the impact of the CFID calibration, and still you see the H0 values also over there. So
thank you.
Okay, Michele, I have a short question myself concerning the last two papers that you mentioned here, because it's not clear what to me the methodologies that have been used. Of course, for Ketane et al., for obvious reason, I perfectly understand. We use surface brightness and Cephase to calibrate I1A and to measure H0. But apparently, in the other paper by Blakesley, they don't use supernova 1A to measure H0. Is that right?
Yeah.
So they use surface brightness,
exactly,
Cephase, and the tip of red giant branch.
Yeah, yeah.
And
so
obviously, at this point, since this distance indicators have a short range, they need to be very accurate in measuring the peculiar velocities.
Yes, yes, indeed.
And at that point, I'm a little bit skeptical on this small 2.4 delta H naught due to systematics, because it's not that easy to measure with accuracy the cosmic flow velocity, the peculiar velocities. However, we can have time to discuss this.
Yeah, yeah, sure. Yeah, you already answered your questions.
Okay. So next speaker is Michele Moresco, and he's going to talk about the cosmic chronometers. Excellent title, I would say.
Thanks.
Please.
Okay, can you see it?
Yes.
Okay. So thank you, Massimo, for the introduction. In this talk, I would like to give you a general overview about the cosmic chronometer, which are an independent cosmological probe to determine and measure the expansion history of the universe. Here in the first slide, I list the main collaborator to this analysis. And in these slides, I briefly show what I will discuss about the method, the selection, the systematics involved, a few measurements that we did in the past, and the cosmological constraints that we obtained. So if you want to go further in the details, I left here the main reference so you can have a look. So to start, what is the basic idea of cosmic chronometer? What have we seen basically in this parallel session? What we saw is that for most of the cosmological probes, the main point is to find some standard quantity. So some objects, some tracer with some standard properties that we can study as a function of redshift or as a function of look-back time. And the point is that if we have objects with standard properties, for example, standard luminosity or standard length, if we study them as a function of redshift, basically these allow us to disentangle the intrinsic evolution from the evolution induced by the expansion of the universe, and therefore allows us to determine the expansion of the universe. The cosmic chronometer idea follows the same path, but instead of studying the luminosity or the length, here we are studying time. So we are studying in particular how much the universe have aged between a couple of times in order to determine the expansion history of the universe. So the cosmic chronometers, in a nutshell, the basic idea is that they are based on chronometers. And here I want to underline this because in the literature, they are often referred also as cosmic clocks. I actually prefer to call them cosmic chronometers because this gives better the idea behind. Because the difference between a chronometer and a clock is that they are both devised thought to measure time, but while clocks measure absolute time, the chronometer is a device which is actually optimized to measure very precisely differences of times, not absolute times. And the basic idea of cosmic chronometer is exactly this, because in 2002, Jimenez and Loeb proposed this equation in which you see that the main variable in this equation is this dz over dt, which is basically the inverse of the differential evolution of the universe in a redshift beams. And the point is that if we are able to measure this quantity here, we have a direct and cosmology independent determination of the Hubble parameter, because here the only assumption that we are making is a Friedman and Robertson-Walker metric, nothing else. And this is one of the main differences with other cosmological probes. So to describe the method in a little bit more details, so here I've put the age of the universe as a function of redshift, and as we know, this relation depends on the cosmological parameters. Here I've put a few values for omega matter to see how it changes. And the point is that if we are able to measure in some redshift beams this age of the universe, the point is that if we measure the difference between a couple of redshift of the age of the universe, so if we measure how much the universe have aged between a couple of redshift beams, this directly translates in a measurement of the Hubble parameter without any further assumption. And we can make this for many other points. And so the main point here is that we are not interested in the absolute normalization of this curve, but just in the slope, so in the derivative of this curve. So the point now is how can we be able to determine this quantity here, because here we want the age of the universe. So a naive approach would be basically to fill this kind of plot with all possible ages of all objects. And if we are able to fill it completely with all the objects of the universe, if we take the oldest object at this redshift, this can give us some understanding of which is the oldest object at each redshift, and so we can determine it. But we can do better than this. And in particular, we can try to select optimal tracer, which can be homogeneous. And being homogeneous, they trace basically how much the universe has evolved. And if we are able to determine this oldest object in the universe at each redshift by measuring how much they change in age between a couple of redshifts, we can determine the Hubble parameter. So here I would like to discuss a little bit further some of the main points of the method to provide you a better understanding of it. So I will briefly discuss about tracer, how are we able to select them. I will talk about the age, which is the main uncertainty in the equation, and how robustly are we able to measure it. I will discuss the systematics involved in the method, and finally, I will try to give you some pros and cons of the method with respect to the other methods. So about the tracer, here I leave you the main reference in which we have studied this topic. What has been found in the literature, so firstly proposed and then verified, is that the best tracer to be used as cosmic chronometers are very massive and possibly evolving galaxies. The reason being that we have found that this system not only are the oldest object in the universe at each redshift, but we also found that the more massive we select this object, the more synchronized their star formation, their formation become. So if we select completely passively evolving galaxies, we are selecting objects which have finished their star formation and they are just evolving passively with time. And if we select the most massive of them, we are selecting also those families of objects which have formed in a very specific time frame. And so they are very homogeneous sample. The point is, what do we mean with passive? Because in the literature, there are many definitions of passive galaxies. They can be selected depending on the star formation rate. They can be selected on color, on morphology, also on spectroscopy. The point is that in this paper here, we basically verified that a single criterion is not enough to ensure the purity of the sample. Because if we select based on only one criterion, we are left in our sample with still a significant contamination by star-forming object. And this is not good if we want to use this tracer for cosmological purposes. So what we propose in this paper are a combination of multiple selection in order to maximize the purity of the sample. This is very important because I want here to stress that it's not just sufficient to select red galaxies, but we really need to be sure that our sample is not biased by star formation, ongoing star formation. The second point is, what about the age? Because as I told you before, this is the only uncertainty in this equation here. And the point is that determining the age of the population is a very difficult task. And we know that there are known degeneracies with other parameter. For example, the most known is the metallicity. Here, I want to stress before discussing a couple of points. The first one is that we want to measure DT, therefore the differential age and not the absolute age. So if we are able to find a method which gives us some offset in the absolute age, but a good slope, so a good differential evolution, this will not affect our method. So this is really the quantity that we are interested in. The second point is that in our determination, we need to be sure to make no cosmological assumption, because we don't want to have some measurement which is based on implied assumption. And this is very important because in many evolutionary studies, these cosmological assumptions are usually made, in the sense that in many cases, the age of the stellar population is fixed to be smaller than the age of the universe at a given redshift. The third and most important point is that we have to find some way to break the degeneracies between parameters to measure this DT. And there are various ways that can be explored. We can try to do it to measure this differential age with set fitting. So therefore, from the photometry of the object, this is not so much a reliable method. There has been experiments on trying to determine it with full spectral fitting, and this is more stable and reliable, even if with some degeneracy. We can try to explore focusing on a specific feature in the spectrum, in particular absorption feature, and I will remind you of the talk after me by Nicola Borghi that will discuss this. In my work, what I try to do is to go on another approach. That is, instead of trying to do some kind of fit, my point was to try to see in the spectrum of a galaxy if there is a direct observable that we can try to link to the age of the population. And the observable that we focused on is the D4000, which is this break that we observe in galaxy spectrum at 4,000 angstrom rest frame. And the amplitude of this break, we verified that can be directly linked to the age of the population. And most importantly, for the object and the redshift range to which we are interested in, we can also verify that the relation between this break and the age of the population can be described really well by a linear relation. The nice thing, if we can write a linear relation between the D4000 and the age, is that, as I told you before, we are not interested in the absolute age, but in differential age. So if we differentiate this equation here, we can rewrite this equation basically in this form. And this is an improved version of the previous equation, because in this equation, we manage basically to decouple statistical and systematic effects. Because in this equation, this quantity here, which is the differential D4000 evolution now in a redshift bin, can be directly estimated from the data, as we did, for example, in this paper here. We have some measurement of the D4000 in the redshift bin. If we take the difference between a couple of redshifts, we have directly this quantity here. This parameter A here, instead, is something that needs to be calibrated with stellar population synthesis models. And what we can do is to try to find as much models as possible to try to compare the results, to try to estimate this calibration parameter from different models, and use these to determine the Hubble parameter and also to determine the uncertainty in this assumption. So the third point is, what about systematics? And I will be rather quick, even if this part took us a lot of effort, especially in the latest year. There might be many systematic effects that can bias the results. The first and foremost, of course, as I described before, is that we rely on some calibration parameter that depends on stellar population synthesis model. So how much our results depend on the assumed model need to be assessed. We need to assess if, despite the good selection, if we still have some young population or star-forming population in our sample, how much these might affect our determination. We can be dependent on the progenitor bias, and so on a differential evolution of the population as a function of redshift. The point is that all these effects have been studied in detail. I don't have time now to describe. These are described basically in this paper. The end of this effort was basically that we were able to provide a total covariance matrix that takes into account all these possible sources of effect. So both the statistical, that depends on metallicity, star formation history, contamination of the young component, and so on and so forth. So we basically managed to propagate all the possible sources of systematic effect, and we have now a covariance matrix that takes these into account. So to conclude this first part, what are the pros and cons of this approach? So the pros that I tried to stress in the previous part is that it is a differential approach. And this, I stress again, it is very important because not only we have better accuracy in estimating relative ages rather than absolute ages, but this also helps in minimizing many of the possible systematic effects that I didn't have the time to discuss. The second point is that it is a direct measure of the Hubble constant, which is cosmology independent, because as I tried to show, there are no hidden cosmological assumptions. We don't assume any form, functional form, for the determination of the Hubble parameter. And these make these kind of data ideal to test cosmological models, not only standard cosmological models, but also more strange and with different flavors cosmological model. The cons of this approach is that basically these three. The first one is that we need to ensure precisely the homogeneity of the sample. It is a method that nevertheless relies on a metallicity prior or estimate, because in some way we have to break this degeneracy between the age and metallicity of the population. And finally, we need to take really carefully the dependence on stellar population synthesis models. So to give you...
Michele, 3 minutes.
Okay. I will go a little bit faster on this. This gives you a worked example. This shows for this paper how the evolution of the D4000 looks as a function of redshift. Here the redshift is increasing, going from spectra from the upper part to the lower part. And you can see directly from the observable that this break decreases with redshift. And this can be directly traced more quantitatively in this plot, for which we determine this Hubble parameter. So I will skip a little bit these. These are the data that we explored. And so far, basically, we try to explore most of the publicly available data. And so SDSS, BOSS, and many high-redshift galaxies. And this is the current state of art of the determination of the Hubble parameter. So what we manage in this year to determine as a function of redshift. In this few last minutes, what can be done with this measurement? A lot of things, actually. Because we can use those to explore cosmological model, to do probe combination as discussed previously in other talk, to obtain model-independent estimate of cosmological parameter, to have a word in the Hubble constant tension. And just to show you some quick example, these are a couple of papers that in which cosmic chronometers have been used basically to extrapolate the Hubble constant at redshift 0 with the Gaussian process, so to keep the independence on cosmological models, obtaining compatible results. We also explored how much the constraining power of cosmic chronometers compare with other standard probes, basically demonstrating that even if it's not yet at the level of supernovae, actually the combination between different parameters starts to becoming competitive. So we can start to think of not using some standard probe and to use other alternative probe and obtaining compatible results. We can use it to map the transition redshift in a cosmology independent way. And finally, we can also combine these with other determination here. For example, we combine the measurement of the expansion history with the measurement of the growth to put basically the available data in this plot suggested by Linder in 2017 to try to discriminate different models. And I leave you with my conclusion here. Thank you.
Thank you, Michele. We have time for a couple of questions. Nobody? Raise the hand. Okay, look, I think we have something to discuss at the end during the discussion. So I will move to the next speaker, that is Nicola Borghi.
Thanks. Can you see the screen?
Yes. And he's going to talk about a new measurement of the expansion history of the universe. Very well.
Okay, thank you very much for the opportunity of giving this talk. I hope there will be no connection drops. So what I will present here is basically a practical application of what you have just heard. We try to jointly study stellar population properties of passive galaxies in intermediate universe, especially relying on the publicly available legacy survey, jointly with the cosmological study using the cosmic chronometer approach. So we start this presentation going very fast on the basics of this method that you just heard. Here I want to stress that with a very minimal assumption, relatively minimal assumption, and without assuming cosmological model, we can obtain a direct measurement of the Hubble parameter by studying the differential aging of the universe. So what we need is a homogeneous tracer as a function of redshift to trace the age of the universe, actually the aging of the universe over different cosmic epochs, so that direct measurement of h of z can be obtained, and using these we can discriminate between different models. So I leave here with the pros of this method that I wanted to stress. Here in my talk I will focus on two key requirements to use these galaxies as cosmic chronometers. The first one is that we need a pure sample of passively evolving galaxies, and the second one is that we need a robust determination of their differential aging without relying on cosmological or even hidden cosmological assumptions. So massive and passive galaxies, as we just heard, are characterized by having synchronized and short star formation histories. I want here to discuss what is the observational evidence that we have, and one evidence, I think one of the most important one, is the other observation that I show in this plot. So basically, by studying parameters such as the enhancement of alpha element over iron, the metallicity, and the age of this population, we can learn something about we can reconstruct their past star formation history that you see on the left plot. So basically, more massive galaxies generally are older, have higher metallicity and higher alpha over iron ratios. And I want to stress that alpha over iron is very important because alpha elements are produced by explosions of short-lived high mass stars, while iron elements are mostly produced by type 1a supernovae that require more time to be developed and then to explode. So the high alpha over iron ratio correspond to a shorter star formation history, while a lower alpha over iron ratio can be interpreted as a higher, longer star formation history. So with this in mind, we want to derive a robust constraint on differential age. There are different methods. Photometry is the best and the less cost efficient choice. And however, as clearly demonstrated by many previous works, there is the problem of degeneracy between some parameters. Most of them, the degeneracy between age and chemical content. You can see here that the constraints obtained with the photometric only information are very broad. And especially the age cannot determine as well as metallicity. Things can be improved with the spectral information, the full spectral fitting method that is now the most used and will be the most used has some requirements of high computational cost, and I will discuss some the generalities that need to be understood. And so we relied on the old standard method of the Lick indices, so focusing on a combination of spectral indices to derive galaxy ages, combined with also abundances, in particular metallicities and alpha over iron abundances. So extended the work that I just showed before. I will describe very fast the legacy survey, that is a ESO survey, sorry. And this is the coverage in the sky, but I want you to focus on the right plot that shows the spectral coverage. So basically the region here, mostly between 4,000 and 4,100 angstrom, is the spectral region for which we have an homogeneous coverage over the redshift. And so we can use an homogeneous part of the spectrum to derive galaxy ages. And I will explain later why this is very important, not to use different part of the spectrum to derive galaxy ages. However, this range is very small, is limited, and this is one of the major efforts that we did, is to derive the robust constraints of this very limited range. Collection of passive galaxies need the cross different criteria. As you just heard, we need to be very sure that these galaxies are really passively evolving. We combined the photometric method that makes use of near ultraviolet R and J photometric bands with spectroscopy, especially in particular the information on the oxygen 2 line, requiring low equivalent with less than 5 angstrom. And we also visually inspected each of the remaining spectra in order to be sure that no hidden emission line components were there. And we end up with 350 galaxies having a very low specific star formation rate. Just to have a reference, the value that is usually adopted in the studies is minus 11. We have only very few galaxies with the specific star formation rate higher than minus 11. You can find here the distribution on redshift, and this shows one of the major limitations of this work, that is the unhomogeneous coverage as a function of redshift, as well as the limited statistic that we have. And here there is also the distribution in sigma and the star formation rate. So just mention, during this analysis, we developed a software that we made publicly available to study specific spectral indices. If you are interested, you can find the code available on GitLab. And this allowed us also to investigate some newly defined pseudo-Lick indices that are calcium H and K line. And a little spin-off, how can we be sure that these galaxies are really passive? Well, the calcium H over K line ratio can tell something about the passive status, because actually measuring this region over this region can trace episodes of very recent or young star formation, less than 1 gigayear. Because if you look this passive spectrum in violet, here I highlight the value of the calcium K indices, and this value is lower in star formation, in galaxies with a high star formation. However, this does not happen in the calcium H line because there is the infill of the Balmer epsilon. And so by comparing these two lines, we can say something about the status of these galaxies. And we demonstrated in the work that was submitted a few days ago that this indicator actually correlates with a bunch of and very well-established other indicators like UVJ, UVJ, and also correlates with the star formation rate. So we analyzed the ISG/K ratios of our galaxies that here are outlined with black borders, and we found that these ratios are very small and compatible with being passive. I will give further information if you're interested. So to make this short, we analyzed each of these galaxies with Thomas Maranstone and Johansson models that assume a single bar star formation, as usually done in this kind of work. And we use an optimized set of indices, ensuring that each galaxy had this specific set of indices. And we, and I want to stress this, did not assume any cosmological prior, for example, on the maximum allowed age. And here is an example of the posterior distribution coverage of one of our galaxies that we analyzed. And we end up with 140 galaxies constrained with typical error on the age of 0.4 gigayear and typical error on metallicity and alpha over iron value of 0.05. So with these galaxies, first of all, we tried to see if the correlation with the stellar velocity dispersion, or equivalently with the mass of this system, were in place, and we find positive answers. So already 7 gigayear ago, there were positive relation between age, metallicity, and alpha over iron values, confirming that these galaxies and this population of galaxies is very similar to the one observed locally, and also consistent with the mass downsiding scenario, so that more massive galaxies are older and have higher metallicity and higher alpha over iron values, even if with a very large scatter, mostly due to the limited statistic that we have. But this is very important because for the first time at intermediate redshift, so redshift 0.7, we saw a positive relation with the alpha over iron and the sigma. So the most important the most important result is the study of these population properties over redshift, because we want to use the differential aging of this population to study and to learn something about cosmology. So we divided these galaxies in 2 mass bins and in 4 bins in redshift, and you can see that this is a very remarkable result, that we obtained 2 almost parallel age redshift relation that we interpreted as due to the aging of the universe, and we do not obtain any significant evolution in redshift, confirming again that these galaxies are passively evolving and their chemical content does not evolve over these cosmic epochs. And so I will move to the results. So we use these 4 points. We took a couple of points at both high mass and low mass regimes to derive a new measurement of the Hubble parameter. And here are the results. So this is the distribution of our points in gray in the age redshift plane, the binned results in the age redshift plane, and the average obtained doing the weighted average of the 4 H of dead measurement that were obtained between non-consecutive couple of points. And these new results follows very well the previous points that were obtained in the literature, and mostly with a different method, mostly with the D4000 method that you've just heard, and a few of them with full spectral fitting techniques. And I want to stress here that this work is important because it gave us the possibility of exploring the effect of having different combination of indices, even if these limit the number of constrained galaxies because of the limited wavelength coverage that I've anticipated before. And I think that this is a very interesting example to show that what it matters in the cosmic chronometer approach is not the absolute age, but the relative age of these galaxies. So we analyzed the slope of age redshift relation obtained with different combination of indices, and they differ by plus or minus 1 gigayear. However, if we study their slopes and therefore also the Hubble parameter measurement, we obtain very compatible result within 0.2 sigmas. Even if we have reason to prefer the value combination because it maximizes the spectral coverage and number of galaxies. And I want to spend a few words also on the analysis of systematics that we did. We tried to repeat the analysis with a different set of models, the Vazdekis model. Here you see the percentage difference over redshift, because we are not interested in actually in their absolute values, but if there is a systematic trend over redshift, and yeah, you see that the scatter is very high, but there is no significant slope, and so this translates in final measurement that consistent within 1 sigma. And these models gave us the possibility also to analyze a more extended star formation rate. This is a point that is usually asked, because our results assume single bar star formation that are not realistic. But the problem is with assuming more extended star formation rate, and this point should be further assessed in the future, that we have a strong degeneracy between age, and you can see, and the tau, that is basically the duration of this star formation episode. That usually this degeneracy is relieved by assuming a prior on the age, but we do not want that. We do not want to introduce cosmology in our analysis, and so these should be further explored in the context of a cosmic chronometer. So break age tau degeneracy without using cosmological prior. And finally, I want to introduce another kind of study that can be done. Here we rely on the absolute ages. By using this relation, we can model the age of the universe versus redshift relation by using some cosmological parameters. And we can say that the upper mass population follows and traces these TU with a constant offset. This is actually the cosmic chronometer approach, so that these galaxies can trace homogeneously the TU over Z. Then we use also the low mass relation. I want to highlight also that we say low mass, but actually it's high when compared to star forming and other galaxies. So we are still in high mass regimes, but a lower mass with a constant offset that is computed as the mean as the average between the difference of these points. So we fix delta t, we leave free TF, and with this very simple model, we can say something about the cosmological parameter joined with the TF that can be thought at the formation time after the Big Bang of these galaxies. And this is the simulation.
Nicola, 3 minutes.
Yeah, thank you very much. We can see here some simulation done for the high mass regime. We also include here low mass points just as a reference, but these relations are built for the red points by perturbing each of these parameters singularly. And in this way, we can model and see what are the major degeneracies. For example, you can see that TF, H0, and omega m produce very similar differences in the slopes and the shapes of these age redshift relation. And for example, H0 and omega m, by increasing H0 and by decreasing omega m, we can reproduce the same trend. on the age redshift plane. And so, yeah, the degeneracies are there. And with the current data, we cannot distinguish between different omega 0 and omega A in the CPL parameterization parameters, because the redshift leverage as well as scatter is very high. And this is the result. So we use these two relations, as I just explained, and we derived jointly some constraints for H0 omega m, assuming a lambda CDM universe, and this formation time. And you can see here that by assuming flat priors, we let's say these results have a very large error bars, are very democratic, but they tend to prefer higher values of H0. If we assume a prior, a Gaussian prior using Planck data on the omega m, that this method, as you can see, is not very well able to constrain, we obtain even higher H0 value. However, I should point that the degeneracy between TF and H0 should be further explored, because here the main limitation is that we are studying a very limited redshift range. This, I think it's a promising technique, but in order to say something about this trend, we should have we should study homogeneously the redshift, high redshift range with the same survey, same parameters, same method to compute ages, because as I've explained before, if we choose different combination of indices because we are limited to spectral coverage limitation, we obtain different absolute values of age. So this method relies on absolute values, and for this reason it is important to have a homogeneous coverage and to use an homogeneous survey. However, there are no dedicated surveys that will be able to study high number of galaxies in a high redshift range, at least in the near future. So I leave you with the summary of the work that, as I said, jointly studied the stellar population, detailed the stellar population of 140 passive galaxies and their underlying cosmology. Thank you for listening.
Thank you very much, Nicola. There are questions? Well, I have a question myself. That refer also to the previous talk by Michele. Basically, I was not familiar with chronometers, cosmic chronometers, before listening to your talks, and now the methodology is very clear. What I'm a little bit mystified is about the accuracy that you can achieve with these methods. It seems to me very indirect, and that takes into the business uncertainties and systematics, but maybe I'm wrong. Can you, Michele or Nicola, comment about this, please?
Yeah, I will do a brief comment related to this work. As also Michele anticipated, the major systematic is expected to be the choice of a different stellar population synthesis model and or the assumption of a more extended star formation history. We did what we could do with the currently available models, exploring this rather different approach in the cosmic chronometer field. So the approach of using Lick indices to derive age, metallicity, and alpha over iron. And so we can say that it's related to the degeneracies between ages and chemical content in general should be minimized with this method. But there is still there is still a large analysis to do with these things that I just mentioned. So unfortunately, models available now in the literature are not so many, and we are studying in a parallel analysis different approaches, such like full spectral fitting, to explore in more detail the systematics of assuming different ingredients in the stellar population models. If Michele wants to add something.
Yes, just can you go back to the previous slide that you show before the last one?
This one?
No, the one with the uncertainties in the exactly. Now my question is was much more. No, the previous one.
Okay, sorry.
This one. So my question was basically the following: realistically, how much do you think you can decrease the uncertainty attached to H0, for example, 74 plus 23 minus 16?
So if I comment just briefly on this, the point is also that so in this study we focused on a very specific sample. So this analysis is new in the sense that we explored a different approach and so the method of the leak indices with new ways of approaching this, that is measuring individual galaxies. But this sample was just 140 galaxies. If we extend this method, so we look the cosmic chronometers taking a step back, and so we look at all the measurement with all the other data. For example, in SDSS and BOSS, we are able to collect hundreds of thousands of objects, so 3 orders of magnitude more galaxies. And so in that case, the statistical uncertainty on the determination of the age is reduced significantly, and it's there then where the systematic effect starts to become extremely important and important to handle. So, for example, if one use not only these 4 points, but the entire cosmic chronometers method, one is able to reach an accuracy on the Hubble parameter of the order of, I would say 5 or 6. So we are able to decrease quite a lot these numbers. To go a step below, and so to arrive at a determination which is compatible with Schuss or with Planck, we need to make a step further in the assessment of the systematic, because at this moment the main limitation is that we have many stellar population synthesis model to calibrate. So that uncertainty is the one that is dominating now. But if we are able to compare models and to reduce the range of available models which are provide a good fit, we are able to shrink that kind of error, and therefore to also further reduce the uncertainty of the Hubble parameter.
Thank you, Michele. The other Michele Cantiello, are you there?
Yes.
Yes, because I was asking to you something, but I mean, I was shifting your answer, your possible answer to the discussion, and this is the right
actually
to go.
about the
the point you raised about the peculiar velocities. I have a comment and a follow-up comment. So a comment is that, okay, the authors of that paper, Blakesley and collaborators, they tested various velocity flow models. And what they did, also culling the sample using the different selection approaches, what they found is that the impact using this different methods, these different models on H0 is of the order of 1%, about that. So it's less than 1 kilometers per second per megaparsec on the H0 value. So it's something that to the status of the data we have motivates the small 2.4 systematic. Again, the dominant contribution to that systematic comes from the in that case CFID and the TRGB combined at 0 point. Actually, as I said in my presentation, what is important for these local field distance indicators, actually no, there is something more. This is probably true also for the small impact on H0. It's also true because these galaxies are mostly like the one that Nicola and Michele just discussed. These galaxies are massive red galaxies, but in the low redshift regime. And so they sit in the potential well, typically they sit in potential well of their groups or clusters. So this might also impact less than any other like lower mass galaxy on the estimate on their peculiar velocity. But this is something indirect reasoning. For the future, though, what is very important is that it is true the peculiar velocities for low redshift regime for the 100 megaparsec distance scale is going, is going to be needed to get very accurate, more accurate cosmic flow models, and then that's where the realm of the Vera Rubin Observatory and Euclid is going to play an important role for SBF, because you get at the same time distances and then obviously with some combined data to get velocities, you can build extremely accurate flow models to update what we have now. Again, what we have now says that the impact on H0 with SPF distances is of the order of less than 1%. The impact of the peculiar velocities. Besides, on the question by Michele for the possible systematics, as I said, there is a completely independent route that we can follow, which is the theoretical calibration. The present calibration relies on empirical calibrations and empirical relations which depend obviously on the primary indicators. But if we use theoretical calibration, that's completely independent from that, and they are consistent. So different stellar population models. Again, we go to the, there's some link between these two things. So the theoretical calibrations, although there is a kind of scatter between the various calibration, the scatter is basically supports what is found from empirical relations. So we don't see really an obvious offset between empirical and theoretical calibrations. Clearly, since in the future we're going to go in the near infrared regime where calibrations are less certain, it is important to get accurate cell population models in those interval of wavelengths. I also am curious, but I don't see Luca, about the number of candidate GRBs within 0.05, say a couple of 100 megaparsec, which have host galaxies that can be targets for SPF. This is a curiosity I had.
Sorry, just a quick reminder that I think in 1 minute the Zoom session will be automatically closed.
Okay.
So maybe. Maybe. No, sorry, you can go, Massimo.
No. I mean, I was proposing to close the discussion. Maybe we can keep going tomorrow, because I have more questions for both Michele's and Nicola and Esther that I couldn't I couldn't interact with her before. Luca, unfortunately, has to cannot be here, and so I hope to see him tomorrow. Okay.
Okay. Great.
Okay.
Michele, your conclusions. The conclusions are yours.
No. I just want to thank all the speakers and hope to see you tomorrow to continue the discussion. Okay. Thank you, everybody.
Buon appetito.
Yes.
That's
bye-bye.
Thank you. Bye-bye.
Bye.
Bye-bye.
Bye.